Deep in the vast ocean of space, a signal older than life itself is still reaching us, a ghostly echo from a star system that died 1 billion years ago. What's astonishing isn't just its age, but the fact that this ancient cosmic whisper is quietly shaping the technology we use every single day. Think about that for a moment. The same forces that once powered distant, long-dead stars are now embedded in the devices in our hands, the satellites orbiting our planet, even the medical tools saving lives in hospitals. This isn't a futuristic fantasy, it's the hidden story of how the universe's oldest remnants are rewriting the rules of modern innovation. Picture a ripple traveling across an endless cosmic pond, a disturbance so faint it's almost imperceptible, yet when it finally reaches us, it carries secrets that redefine what's possible. These echoes, born from the violent deaths of stars, have journeyed across galaxies and epochs, surviving the birth and death of countless worlds. And now they're here, whispering to scientists and engineers, revealing clues that unlock breakthroughs in everything from navigation to energy. It's as if the universe left us a message in a bottle, and we're only now learning how to read it. But how does something so ancient and distant still influence our world today? The answer lies in the way these cosmic echoes interact with the very fabric of reality, how they bend space, distort time, and carry energy in ways we're just beginning to understand. From the precision of GPS signals to the sharpness of medical scans, these remnants of dead stars are woven into the technology we often take for granted. And as we uncover more of their secrets, we're not just learning about the past, we're shaping the future. So let's take a journey together, back to the origins of these extraordinary echoes, forward to the innovations they've sparked, and into the mysteries they still hold. Because the universe isn't just out there, it's right here in the palm of your hand. Long before Earth even existed, in a corner of the cosmos now lost to time, a star many times more massive than our sun burned through its final moments. When it could no longer resist the crushing force of its own gravity, it collapsed inward, then exploded outward in a supernova so powerful it briefly outshone entire galaxies. In that cataclysmic instant, the star didn't just die, it transformed. Its outer layers were blasted into space at nearly the speed of light, carrying with them something extraordinary, the seeds of future technology. That supernova's fury forged elements rare and precious: gold, platinum, uranium, scattering them like cosmic dust across interstellar space. But it didn't stop there. The dying star's core, compressed into an unimaginably dense neutron star, began spinning wildly, sending out beams of radiation so precise they pulse like a celestial metronome. These pulsars, as we call them, became lighthouses of the universe, their rhythmic signals cutting through the darkness for eons. And hidden within those signals were electromagnetic fingerprints, subtle distortions in space-time itself, that would one day become the foundation for breakthroughs we now rely on daily. What's truly remarkable is how these echoes of destruction became blueprints for creation. Those heavy metals forged in stellar explosions, they're now vital components in everything from smartphones to satellites. The precise spin of neutron stars, they helped scientists calibrate the atomic clocks that make GPS navigation possible. Even the faint gravitational ripples left behind by these ancient events are now being harnessed to develop quantum sensors capable of detecting earthquakes before they strike. It's as if the universe recycled its own cataclysms into tools for progress, a cosmic alchemy turning stellar death into technological life. But perhaps the most profound legacy of that long-dead star lies in what we've yet to discover. Its remnants are still out there, whispering clues about the fundamental forces that shape reality. Every time a physicist tunes a radio telescope or a materials scientist tests a new alloy, they're tapping into that billion-year-old echo, unlocking secrets the universe has been waiting to share since before our planet was born. To catch whispers from the dead, scientists have built machines that listen to the universe's oldest conversations. Radio telescopes, with their massive dish-shaped antennas, act like cosmic ears sensitive enough to detect electromagnetic waves that began their journey when Earth was still a molten rock. These signals, stretched and faded by billions of years of travel, arrive as faint crackles in the static. But buried within that noise are patterns so precise they rival the most advanced human-made clocks. Take pulsars, for example. These rapidly spinning neutron stars emit beams of radiation with such regularity that their pulses arrive like ticks of a celestial metronome. Early astronomers, baffled by their rhythmic precision, initially nicknamed them LGM signals, are joking that they might be messages from little green men. But the truth was even more astonishing. These natural timekeepers, born from stellar explosions, pulse with a consistency that makes atomic clocks look crude by comparison. By studying their rhythms, scientists have fine-tuned navigation systems so accurate they can pinpoint your location on Earth down to the centimeter. The real magic happens in the details. When a pulsar signal passes through interstellar gas or warped space-time, its electromagnetic waves bend and twist in telltale ways. Sophisticated algorithms decode these distortions, revealing otherwise invisible cosmic structures like mapping the ocean's currents by watching how they bend sunlight. This same principle now helps engineers correct signal errors in satellite communications and even improves medical imaging, where subtle distortions in scans can mean the difference between spotting a tumor or missing it entirely. What makes these ancient signals so valuable isn't just their age, but their honesty. Unlike human-made transmissions that degrade over time, cosmic echoes follow the unbreakable laws of physics. Their consistency provides a universal reference point, a tuning fork for reality itself. When the Voyager probes needed to calibrate their trajectory beyond our solar system, engineers used pulsar signals as their guide. Today, that legacy continues in quantum experiments where researchers harness neutron star emissions to test theories about gravity's fundamental nature. Yet for all their precision, these signals still hold mysteries. Some pulsars occasionally glitch, speeding up inexplicably before settling back into rhythm, like a record skipping for reasons we don't yet understand. Others emit bursts of energy so powerful they briefly outshine entire galaxies, then vanish without explanation. Each anomaly is a clue waiting to be deciphered, a puzzle piece that could reshape everything from energy storage to material science. The universe isn't just sending us messages, it's challenging us to think differently about the very fabric of technology. Imagine a clock so precise it loses less than a second over 1,000,000 years, not crafted by human hands, but forged in the heart of a dying star. Pulsars, those spinning relics of supernova explosions, don't just tick with uncanny regularity. They redefine what accuracy even means. Their beams sweep across the cosmos like lighthouse beams, some pulsing hundreds of times per second without wavering. When astronomers first mapped these rhythms in the 1970s, they realized something extraordinary. The universe had handed us a navigation tool more reliable than anything on Earth. Atomic clocks, the gold standard for timekeeping, rely on the vibrations of cesium atoms, but pulsars operate on an entirely different scale. Their precision comes from the raw physics of collapsed stars. A teaspoon of neutron star material weighs as much as a mountain, and that incredible density gives their spin a stability no Earth-bound machine can match. Early experiments proved their potential. By tracking the arrival times of pulsar signals, scientists could triangulate a spacecraft's position in deep space with astonishing accuracy, long before GPS satellites orbited our planet. The leap from cosmic curiosity to real-world application came when engineers recognized pulsars could solve a critical flaw in Earth's navigation systems. GPS signals weaken or get disrupted when satellites pass over oceans or polar regions, but pulsar emissions streak unimpeded across the galaxy. Today, missions like NASA's Station Explorer for X-ray timing and navigation technology, Sextant for short, use pulsar signals to guide spacecraft autonomously without needing constant contact with ground control. It's like swapping a fragile, human-made map for one written in the stars themselves. What's next? Picture a future where probes to Mars or beyond navigate by pulsar, their courses corrected in real time by the same beams that once guided ancient mariners. Only now, the lighthouses are billions of years old and light years away. Researchers are even testing pulsar-based systems for interstellar travel, where traditional methods fail. Every pulse carries not just timekeeping data, but a faint imprint of the gas clouds and gravitational fields it passed through, a roadmap of the cosmos etched into radiation. Yet the true brilliance of pulsar clocks lies in their duality. They're both ancient relics and cutting-edge tools, their rhythms echoing across time to shape technologies we're only beginning to imagine. As we harness their precision, we're not just borrowing the universe's timekeeping, we're learning to speak its language. Neutron stars are cosmic laboratories of extremes, places where nature bends its own rules with terrifying elegance. These ultra-dense remnants, packing a sun's worth of mass into a city-sized sphere, generate gravitational forces so intense they twist space-time like taffy. At their surfaces, magnetic fields rage with trillions of times the strength of Earth's, powerful enough to rip atoms apart. Yet within this chaos lies a goldmine for modern science. Researchers studying these stellar corpses have uncovered phenomena so strange they've rewritten textbooks and sparked revolutions in technology closer to home. Take quantum computing. Inside a neutron star, matter doesn't behave as anything we recognize. Protons and electrons get crushed together, forming a bizarre quantum soup where particles act in unison, flowing without friction. This superconducting state, once thought impossible to replicate, now inspires designs for error-resistant quantum bits, the building blocks of next-gen computers. Labs worldwide are mimicking neutron star conditions to create materials that maintain quantum coherence at higher temperatures, potentially unlocking practical quantum machines decades ahead of schedule. Then there's material science. The crust of a neutron star is likely the strongest substance in the universe, a crystalline lattice so dense a sugar cube-sized chunk would outweigh Mount Everest. By simulating these extreme pressures, scientists have engineered metastable alloys with unprecedented strength-to-weight ratios. Some are already being tested in aerospace applications, from turbine blades that resist erosion to spacecraft hulls that shrug off micrometeoroid impact. It's as if we're reverse engineering the universe's own armor, but perhaps the most startling discovery involves time itself. Neutron stars spin so fast their surfaces can approach a quarter of light speed, creating frame-dragging effects that warp local time. Precise measurements of these distortions have refined our understanding of general relativity, leading to calibration techniques that now enhance Earth-based atomic clocks. These improvements ripple through technologies from stock trading networks, where microseconds matter, to deep space navigation systems guiding probes billions of miles from home. What makes these discoveries so transformative isn't just their immediate applications, but how they shift our perspective. Neutron stars force us to confront realities where matter exists in states beyond our earthly experience, where a single magnetic field could power civilization for millennia, or where gravitational waves hum at frequencies we're only beginning to detect. Each observation peels back another layer, revealing universal principles that transcend any one discipline. The same physics that lights up a pulsar's beacon might one day stabilize fusion reactors or enable teleportation of quantum information. We're not just borrowing ideas from dead stars, we're learning to think like the universe itself. Every breakthrough carries echoes of that original supernova, reminding us that destruction and creation are two sides of the same cosmic coin. And somewhere out there, another neutron star's invisible influence may already be shaping technologies we haven't even dreamed of yet. Every time you swipe a touchscreen or send a message, you're interacting with atoms that once roared through space at unimaginable speeds, the scattered remains of stars that died violent, spectacular deaths. The silicon in your computer chips, the gold plating your phone's connectors, even the rare earth elements in your headphones, none of these materials were born on Earth. They were forged in the final moments of massive stars, when unimaginable pressures and temperatures fused lighter elements into heavier ones, then blasted them across the cosmos in supernova explosions. Consider the journey of a single silicon atom in your smartphone. Over 5 billion years ago, it formed deep inside a star 20 times more massive than our Sun, where temperatures exceeded 100 million degrees. When that star exhausted its nuclear fuel, it collapsed inward before rebounding in a cataclysmic explosion, releasing more energy in seconds than our Sun will produce in its entire 10 billion-year lifespan. That silicon atom, along with countless others, got hurled into interstellar space at nearly 10% the speed of light. For eons, it drifted through cosmic clouds until gravity pulled it into the swirling disk that would become our solar system. Eventually, it found its way into Earth's crust, then a quartz mine, and finally a semiconductor factory where it became part of a microchip processing billions of calculations per second. Gold tells an even more dramatic story. Unlike silicon, which forms in relatively common stellar explosions, gold requires something far more extreme: the collision of two neutron stars. These ultra-dense stellar corpses, each packing a sun's worth of mass into a city-sized sphere, create gravitational forces so intense they warp the fabric of space-time. When they spiral together and merge, the resulting kilonova explosion forges gold and platinum in quantities that dwarf entire planetary reserves. The delicate gold wires in your electronics likely began in such a collision billions of years ago, perhaps one that briefly outshone every star in its galaxy. Even uranium, crucial for both nuclear power and advanced medical imaging, owes its existence to these cosmic alchemists. The heaviest elements can only form during supernova or neutron star mergers, where neutron-rich environments allow atoms to rapidly capture extra neutrons before decaying into stable forms. Without these violent cosmic events, Earth's core would lack the radioactive elements that drive plate tectonics, meaning our planet might never have developed continents or oceans hospitable to life. What's truly humbling is realizing how thoroughly these stellar gifts permeate modern life. The europium that makes your screen glow red, the tantalum that stores charge in capacitors, even the copper in your charging cable, all were delivered to Earth by ancient stardust. Space agencies now study asteroid compositions not just for scientific curiosity, but because these celestial bodies contain concentrated deposits of the same rare elements our technology craves. In a very real sense, the future of human innovation still depends on materials created in stellar explosions long before our solar system existed. This cosmic connection goes beyond mere chemistry. The same nuclear processes that power stars now fuel our pursuit of clean energy through fusion research. The quantum behaviors of electrons in semiconductors trace back to principles first tested under the extreme conditions of collapsing stars. Even our understanding of material science constantly references these natural laboratories of extreme physics, because the universe has already performed experiments we could never replicate on Earth. So the next time you hold a device, remember, you're not just gripping plastic and metal, you're cradling artifacts from some of the most powerful events in cosmic history, a direct material link to stars that died so technology could live. Their explosions weren't endings, but transformations scattering the seeds of future civilizations across the light years. And in harnessing these elements, we've become the universe's way of turning stardust into something new, the ability to compute, communicate, and explore the very cosmos that made us possible. That faint hiss of static coming through your car radio when you lose the station. It might sound like meaningless noise, but in 1965, two astronomers realized that kind of interference could rewrite our understanding of the universe. Arno Penzias and Robert Wilson were testing an ultra-sensitive radio antenna at Bell Labs in New Jersey, trying to eliminate every possible source of interference for satellite communications. No matter how they adjusted the equipment, an annoying background hum persisted like microwave static you couldn't tune out. They scrubbed the antenna of pigeon droppings, checked for loose wiring, even shielded against nearby radio stations. The noise remained. What they'd stumbled upon wasn't a technical glitch, but something far more profound. The faint afterglow of the Big Bang itself, cooled over 13 billion years into microwave whispers. This cosmic microwave background, as we now call it, became one of the strongest pieces of evidence for the Big Bang theory. But its discovery had an unexpected side effect. It forced engineers to confront how the universe itself creates interference. Those microwaves permeate all of space, subtly distorting signals from satellites and deep space probes. To compensate, scientists developed advanced error correction algorithms capable of separating cosmic noise from meaningful data, techniques that now help your phone maintain a clear Wi-Fi connection even in a crowded cafe. The irony is delicious. The same interference that once frustrated Penzias and Wilson became a tool for sharper communications. By studying how the universe naturally scrambles signals, researchers designed systems that anticipate and cancel out distortion like noise-canceling headphones for spacecraft. Modern GPS satellites use these principles to maintain accuracy despite solar flares and atmospheric turbulence. Streaming services apply similar concepts to deliver buffer-free video, sorting useful data from cosmic static in real time. What began as an annoyance revealed a fundamental truth. The universe is never silent. Even empty space crackles with electromagnetic remnants of ancient events, supernova shockwaves, colliding black holes, the slow spin of neutron stars. Each contributes to a cosmic symphony of noise that we've learned not just to hear but to decode. The next time your video call stays crisp during a storm, thank those long-ago microwaves and the curious scientists who turned cosmic clutter into a cornerstone of modern tech. Penzias and Wilson's antenna, now preserved at the Smithsonian, didn't just discover the echo of creation, it taught us to listen past the noise and find the signals that matter. Their Nobel Prize-winning accident proves that sometimes the most transformative breakthroughs come not from what we set out to find, but from the static we can't ignore. Black holes don't just swallow light, they twist the very fabric of reality into knots. When two of these cosmic monsters spiral toward each other, their collision sends shockwaves through space-time itself, ripples so powerful they stretch and squeeze everything in their path, including the atoms in your body. These gravitational waves, first detected in 2015 by the Laser Interferometer Gravitational Wave Observatory LIGO, travel across the universe at the speed of light, carrying encoded information about the most violent events since the Big Bang. But here's the twist. Scientists now believe these echoes of destruction could hold the key to protecting our most sensitive data from hackers and cyber threats. The connection lies in chaos specifically, how black holes scramble information beyond recognition. When matter falls into a black hole, its properties get stretched and smeared across the event horizon in a process called quantum scrambling. Unlike ordinary encryption, which relies on mathematical complexity, this cosmic chaos is fundamentally unpredictable, a feature that's caught the attention of cryptographers. Researchers at institutions like the University of Chicago and Caltech are modeling black hole physics to create encryption algorithms that mimic this natural randomness. The result, codes that don't just resist cracking, they become mathematically impossible to break without the exact quantum key. Much like how matter swallowed by a black hole can't be reconstructed without knowing its precise state before falling in. One breakthrough came from studying how gravitational waves interact with their environment. As these ripples pass through interstellar gas or warp around other massive objects, they pick up subtle distortions, unique fingerprints that could inspire new error correction methods for data transmission. Imagine sending a message where any attempt to intercept it would distort the signal like space-time bending around a black hole, alerting the recipient to tampering. Early prototypes using this principle are already being tested in quantum communication networks, where security is paramount. But the real game changer might be holographic encryption, inspired by the holographic principle in black hole physics. This theory suggests that all the information about objects swallowed by a black hole gets encoded on its two-dimensional surface, like a cosmic DVD. Scientists are now applying this concept to data storage, developing systems where information isn't stored in traditional bits, but as interference patterns, akin to gravitational wave echoes, that can only be decoded with perfect knowledge of the encryption geometry. Banks and governments are closely watching these developments, as the method could render traditional cyber attacks obsolete. What makes black hole physics so valuable isn't just its complexity, but its universality. The same rules that govern the collision of stellar remnants a billion light-years away also apply to the quantum states of particles in a lab. By borrowing these cosmic blueprints, we're not just building better locks, we're learning to write in the universe's native language of entanglement and uncertainty. And somewhere in the distant future, the same ripples that once signaled a star's death may silently guard the secrets of civilizations yet to come. Deep in the swirling arms of our galaxy, invisible threads of magnetism weave between the stars, remnants of supernova that exploded when Earth was still young. These interstellar magnetic fields, stretching for light years, don't just chart paths for cosmic rays, they've quietly revolutionized how we store every photo, document, and memory on our devices. It turns out the Milky Way has been running the universe's oldest data storage system for billions of years, and we're only now learning to read its instruction manual. Take a hard drive apart, and you'll find a landscape eerily similar to deep space. Tiny magnetic domains on its platters align in precise patterns, much like interstellar dust particles lining up along galactic fields. Both systems rely on the same physics, the ability of magnetized materials to maintain stable orientations until deliberately flipped. Early hard drives struggled with bit rot, where thermal energy would randomly scramble these alignments over time. But when physicists studied how cosmic magnetic fields persist for millennia despite chaotic stellar winds, they discovered nature's solution: microscopic grain boundaries that lock magnetic orientations in place. Modern hard drives now use similar nanostructures, boosting data retention from years to decades. The real breakthrough came from observing how supernova shockwaves amplify magnetic fields. These stellar explosions don't just create chaos, they generate astonishingly organized patterns, like a whirlpool forming in stirred water. By mimicking these self-reinforcing loops in drive firmware, engineers developed error correction algorithms that automatically stabilize weak magnetic signals. Your laptop now uses code inspired by stellar physics to prevent file corruption, essentially giving data the same longevity as those ancient galactic fields. Perhaps most astonishing is how interstellar magnetism inspired three-dimensional storage. In space, magnetic fields don't just run flat along a plane. They twist into helical structures around nebulae, creating layered patterns of information. This cosmic architecture led to heat-assisted magnetic recording hammer technology, where lasers temporarily soften tiny storage regions, allowing data to be written vertically at unprecedented densities. A single square inch of a modern drive can hold terabytes this way, equivalent to stacking entire libraries in the space of a sugar cube, all thanks to designs borrowed from star-forming regions. But the galaxy's lessons don't stop at hardware. The way interstellar fields transmit information across light years without wires has influenced wireless charging and near-field communication. Your contactless payment card uses principles first observed in the polarized radio emissions from pulsars, another case of the universe handing us a billion-year-old patent. Even cutting-edge research into DNA data storage draws from how cosmic fields preserve information in the spin states of hydrogen atoms drifting between stars. What makes these celestial blueprints so valuable is their stress testing. Galactic magnetic fields have endured radiation storms, gravitational tides, and collisions that would vaporize any human-made device. By reverse engineering their resilience, we're not just building better hard drives, we're learning how to encode knowledge that could outlast civilizations. Some researchers speculate future archival systems might use synthetic meteorites with crystalline structures patterned after interstellar dust, creating time capsules that could survive for geological epochs. The next time you save a file, remember, you're participating in a tradition as old as the galaxy itself. Those invisible magnetic whispers between the stars didn't just shape planets and guide cosmic rays. They taught us how to turn fleeting electrical pulses into memories that can span generations. In a very real sense, every hard drive is a tiny piece of the cosmos, humming with the same forces that once sculpted the Milky Way. Among the most violent events in the cosmos, gamma-ray bursts unleash more energy in seconds than our sun will emit in its entire lifetime. These catastrophic flashes, marking the deaths of massive stars or collisions of neutron stars, flood space with radiation so intense it can sterilize entire galaxies. Yet hidden within their destructive power lies a paradox: the same physics that makes these bursts lethal across interstellar distances now helps doctors peer inside the human body with unprecedented clarity. When astronomers first detected gamma-ray bursts in the 1960s, military satellites mistook them for nuclear weapons tests. The signals were that powerful. But as scientists unraveled their origins, they discovered something remarkable. These bursts produced gamma rays with precise energy signatures, like fingerprints revealing the elements involved in the explosion. That discovery became the foundation for positron emission tomography (PET) scanning, where patients received tiny amounts of radioactive tracers that emit gamma rays as they decay. Just as astronomers decode stellar explosions by analyzing gamma-ray spectra, doctors map metabolic activity in organs by tracking these subatomic signals. The parallels run deeper. Gamma-ray bursts travel billions of light-years through turbulent space, yet arrive with their energy signatures intact. a property medical engineers now mimic to sharpen diagnostic images. PET scanners use detectors originally designed for astrophysics research, with materials like lutetium oxyorthosilicate crystals that convert gamma rays into light pulses with extraordinary precision. These same crystals once helped telescopes distinguish between different types of cosmic explosions. Now they identify cancerous tumors as small as a grain of rice. What makes this crossover so transformative is the way it turns destruction into detection. In space, gamma-ray bursts often signal the birth of black holes, events that shred matter beyond recognition. But in hospitals, gamma emissions reveal the body's most delicate processes, from glucose metabolism in brains affected by Alzheimer's to blood flow in damaged hearts. The tracer molecule fluorodeoxyglucose, used in 90% of PET scans, contains fluorine-18, an isotope produced naturally in supernova and artificially in particle accelerators that mimic stellar physics. Recent breakthroughs push this synergy even further. Astrophysicists studying how gamma rays scatter off interstellar dust have helped improve time-of-flight PET scanners, which measure gamma ray arrival times to pinpoint abnormalities with millimeter accuracy. Meanwhile, algorithms developed to filter cosmic noise from telescope data now enhance medical images by distinguishing between healthy tissue and disease. The same computational techniques that map the structure of gamma-ray bursts today generate 3D visualizations of neurotransmitter activity in living brains. Perhaps the most poetic twist lies in the timescales involved. A typical gamma-ray burst lasts mere seconds, but its afterglow can be studied for weeks. Similarly, the radioactive tracers used in medicine have half-lives measured in hours, long enough to perform scans, yet short enough to minimize radiation exposure. This careful balance between persistence and decay, first observed in dying stars, now defines modern nuclear medicine. As telescopes like the Fermi Gamma-Ray Space Telescope discover new varieties of these cosmic explosions, their findings continue to ripple through hospitals worldwide. Each burst cataloged adds to our understanding of gamma-ray interactions, knowledge that quietly upgrades imaging technologies back on Earth. The universe's most violent deaths have become medicine's most delicate diagnostic tools, proving once again that even in destruction, there are blueprints for healing. Every second, invisible bullets from deep space pierce through your body and your devices without you ever noticing. These aren't science fiction weapons, but cosmic rays, high-energy atomic fragments accelerated to near light speed by exploding stars millions of years ago. Most pass harmlessly through Earth's atmosphere, but occasionally, one strikes a silicon atom in your phone or laptop with enough force to flip a single 0 to a 1 in its memory, a phenomenon called a bit flip. In 1998, a single cosmic ray famously caused a voting machine in Belgium to award 4,000 extra votes to a candidate who didn't exist. What sounds like a quirky glitch reveals a profound truth about our technological vulnerability. Early programmers assumed computer memory would behave predictably, but the universe had other plans. As chip components shrank to nanometer scales, these random bit flips went from rare annoyances to critical threats. A single corrupted byte could crash an airliner's navigation system or transfer millions to the wrong bank account. The solution emerged from an unlikely marriage of astrophysics and computer science, error-correcting codes inspired by how nature itself maintains information integrity across cosmic distances. The breakthrough came from studying how DNA preserves genetic information despite constant radiation bombardment. Just as living cells use redundant base pairs to detect and repair mutations, engineers implemented parity bits, extra digits that act like cosmic ray alarms. Modern error correction goes far beyond simple redundancy. Advanced algorithms like Reed-Solomon coding, originally developed for deep space communication, can reconstruct entire corrupted files from fragments, as if reassembling a shredded document by recognizing the patterns in the tiers. Your smartphone now uses variations of these protocols billions of times per second, silently fixing errors before they disrupt your photos or messages. The most demanding applications reveal these systems' true sophistication. Spacecraft like the James Webb Space Telescope experience 10 times more cosmic ray hits than Earth-bound devices. To compensate, engineers borrowed techniques from quantum computing, where maintaining coherence amidst interference is paramount. Webb's systems employ hierarchical error correction, layers of verification resembling how pulsars maintain timing accuracy despite external disturbances. Similar architectures now protect financial networks, where a single undetected error could trigger cascading market chaos. Perhaps the ultimate irony lies in cloud storage. The vast server farms holding humanity's digital memories are increasingly built underground not just for security, but because Earth's crust provides the best cosmic ray shielding. Yet even these bunkers rely on error correction algorithms derived from studying how information survives interstellar space. The universe's randomness didn't just challenge our technology, it taught us how to build systems resilient enough to explore that very cosmos. So the next time your laptop survives a coffee spill or your photos remain intact for years, remember, you're benefiting from a silent war against invisible stellar shrapnel. Those ancient supernova didn't just create the atoms in your devices, they forced us to make those devices robust enough to handle their lingering fury. In scrambling our bits, cosmic rays gave us the tools to protect them. When a star's light passes through a prism, it doesn't just split into colors, it tells a story written in missing lines. These dark gaps in the rainbow spectrum, first noticed by physicist Joseph von Fraunhofer in 1814, turned out to be cosmic barcodes. Each element in a star's atmosphere absorbs specific wavelengths, leaving telltale shadows that reveal its chemical makeup across light years. What began as a tool for decoding starlight now powers the lasers in your grocery store scanner, your Blu-ray player, even the fiber optic cables carrying this video to your screen. The universe handed us a key to its elemental composition, and we turned it into a cornerstone of modern technology. The magic lies in how atoms and light interact. When starlight passes through a gas cloud, electrons in the atoms there jump between energy levels, swallowing precise photon wavelengths. These absorption lines became Rosetta Stones for astronomers, but their true potential emerged when scientists reversed the process. By energizing specific materials to emit light at those same wavelengths, they created lasers with surgical precision. The ruby laser, one of the first practical models, worked because chromium atoms in the crystal emitted light matching their own absorption lines, a closed loop of atomic behavior first observed in stars like Betelgeuse. Today's laser applications read like a tribute to stellar spectroscopy. The helium-neon lasers in barcode scanners, their red glow matches the spectral signature of neon observed in planetary nebulae. The erbium-doped fiber amplifiers that boost internet signals through undersea cables, they exploit the same rare Earth element transitions astrophysicists cataloged while studying stellar atmospheres. Even advanced quantum cascade lasers, used for detecting explosives or monitoring pollution, tune their emissions using principles derived from how molecules absorb infrared light in interstellar clouds. Perhaps the most profound crossover happened in medicine. The excimer lasers that reshape corneas during LASIK surgery emit ultraviolet light at wavelengths first identified in the spectra of dying stars where highly excited molecules like argon fluoride naturally form. By mimicking these cosmic conditions in controlled discharges, doctors gained a tool capable of removing tissue one microscopic layer at a time, with less heat damage than a traditional scalpel. Similarly, the carbon dioxide lasers used in skin resurfacing trace their lineage to the vibrational spectra of molecules observed in comet tails and star-forming regions. This synergy keeps evolving. Astronomers recently discovered stars with bizarre spectral lines indicating quantum behaviors previously thought impossible, findings that laser physicists are now testing in lab-grown crystals. Meanwhile, the hunt for exoplanet atmospheres has refined our ability to detect faint absorption signals, techniques now adapted for LiDAR systems that map forests or monitor carbon emissions from space. The same algorithms that separate a star's light from its planets now help autonomous cars distinguish between pedestrians and street signs in fog. Every laser pulse carries an invisible legacy, the fingerprints of elements forged in stars, analyzed through telescopes, and reborn as focused beams that stitch together our digital world. The light that once revealed the composition of distant suns now scans packages, transmits movies, and corrects vision, proving that sometimes the best way to see farther is to look closer at what the stars have already shown us. Not too hot, not too cold, the universe has a knack for finding perfect balances, and nowhere is this more evident than in the way dead stars influence our technology. Imagine a cosmic thermostat, fine-tuned over billions of years, where the remnants of stellar explosions provide just the right amount of energy, materials, and electromagnetic influence to spark innovation without frying our circuits. It's as if the cosmos itself calibrated these echoes to sit in a technological sweet spot, a Goldilocks zone where destruction becomes creation. Take radiation, for example. A pulsar's deadly gamma-ray beams would sterilize planets light years away, yet by the time those same signals reach Earth, they've diluted into precise timekeeping tools. The difference between a navigation aid and a death ray comes down to distance and decay. The universe's natural volume knob turned to exactly the right level. Even the rare earth elements we rely on, like neodymium in headphones or europium in screens, arrive in concentrations that are useful but not overwhelming. Too much gold or platinum in Earth's crust, and these metals would lose their value and functionality. Too little, and we'd never have discovered their conductive and catalytic properties. The supernova that forged them scattered their gifts with cosmic restraint. Magnetic fields tell a similar story. Neutron stars generate fields trillions of times stronger than Earth's, powerful enough to rip molecules apart. Yet their influence at interstellar distances subtly aligns particles in ways that inspired error correction algorithms for hard drives. It's the difference between standing next to a hurricane and feeling its breeze a continent away. A force that could destroy up close becomes a guiding whisper when properly attenuated. Engineers now mimic this balance in MRI machines, where magnetic fields strong enough to image individual tissues must be carefully contained to avoid harming patients. The real marvel is how these influences interact. Cosmic rays that flip bits in computers also seed clouds in our atmosphere, regulating Earth's climate. The same radioactive elements that power deep space probes heat our planet's core, driving the geodynamo that generates our protective magnetic field. Even the gravitational waves from colliding black holes, while imperceptible to humans, have inspired vibration-dampening systems for semiconductor factories where a single tremor can ruin a microchip. The universe doesn't just provide raw materials, it offers a masterclass in equilibrium. This delicate dance raises a tantalizing question. Is our technological progress somehow encoded in the universe's constants? The weak nuclear force that governs radioactive decay is precisely strong enough to heat planetary cores, but not so strong as to make stars burn out instantly. The electromagnetic force allows for complex chemistry without making every molecule unstable. Even the expansion rate of the universe seems fine-tuned too fast, and matter would never coalesce into stars, too slow, and everything would collapse back into a singularity. We're not just borrowing from dead stars, we're existing in a niche they helped create. Future breakthroughs may depend on recognizing these cosmic balances. As we push quantum computing to its limits, we're learning to harness superposition states that mirror how particles behave near neutron stars. Clean fusion energy research looks to the same proton-proton chains that power stars, seeking to replicate their stability at manageable scales. Every time we hit a technological ceiling, the universe whispers clues about how it solved similar problems billions of years ago. The Goldilocks zone isn't just a place, it's a principle, reminding us that the most powerful innovations often lie in the art of calibration rather than raw force. So the next time your phone seamlessly switches between Wi-Fi and cellular signals, or a GPS pinpoints your location within steps, remember, you're witnessing a cosmic balancing act perfected over eons. The universe didn't just give us stardust, it gave us the perfect recipe for turning chaos into precision. And somewhere out there, another dead star's echoes may already be shaping technologies we've yet to imagine, waiting for us to find their rhythm in the grand interstellar dance. Dark matter doesn't just hide in the shadows of the cosmos, it sculpts the universe from behind the scenes. Though invisible and intangible, its gravitational fingerprints twist galaxies into spirals, bind clusters together, and dictate the large-scale structure of everything we see. But what if this enigmatic force, which refuses to interact with light or matter as we know it, holds clues to safeguarding our digital world? Scientists are now peering into the darkness not just to understand the cosmos, but to borrow its most elusive secrets for cybersecurity. The connection lies in the way dark matter communicates, or rather, how it doesn't. Unlike ordinary matter, which constantly emits and absorbs photons, dark matter's interactions are so faint they evade detection entirely. It's the ultimate stealth material, shaping the universe without leaving a trace. Cryptographers have taken notice, asking, could we design a network that mimics this cosmic subtlety? One where data flows like dark matter's gravitational whispers, detectable only to those who know exactly where and how to listen. Early experiments suggest the answer might be yes. Quantum networks inspired by dark matter's behavior use entanglement, a phenomenon where particles mirror each other's states instantaneously across distances, to create communication channels that can't be intercepted without disrupting the signal. It's akin to how dark matter's presence is inferred only when a galaxy moves differently than visible matter predicts. Any attempt to eavesdrop would alter the quantum state, triggering alarms like a cosmic burglar tripping a silent security beam. Even more intriguing are dark encryption protocols modeled after the universe's hidden scaffolding. Traditional encryption relies on mathematical complexity, but dark matter's influence operates through geometry, warps in space-time that guide motion without direct contact. Researchers at institutions like MIT and CERN are testing lattice-based cryptography, where data hides in multidimensional structures as unreachable as dark matter's particles. Crack one layer and another twists into place, mirroring how galaxies orbit within invisible halos they can never touch. The real breakthrough may come from dark matter's most puzzling feature, its refusal to interact. Most particles collide, scatter, or decay, but dark matter passes through everything like a ghost. Engineers are now developing quiet data packets that mimic this, slipping past conventional cyber defenses undetected. Military satellites already use variants of this tech, transmitting messages via neutrinos particles that, like dark matter, traverse planets without stopping. Future civilian applications could make credit card transactions as untraceable as dark matter's journey through a star. Yet the greatest lesson dark matter offers isn't just about hiding data, it's about redefining trust. In cosmology, we trust dark matter exists because the universe behaves as if it's there, even if we can't see it. Similarly, next-gen cybersecurity may shift from verifying senders to trusting the unbreakable physics of the transmission itself. Imagine a web where authenticity isn't proven by passwords or fingerprints, but by the fundamental laws that govern quantum spin or space-time curvature. As we unravel dark matter's mysteries, we're not just mapping the cosmos, we're downloading its security protocols. The same invisibility that once frustrated astronomers now inspires a revolution in protection, turning the universe's most elusive material into a blueprint for perfect secrecy. And somewhere in the darkness between stars, the very thing that makes the universe hold together might soon keep our most sensitive information safe. Finding planets orbiting distant stars is like spotting a firefly next to a searchlight. The glare from the host star drowns out any faint reflected light. For centuries, astronomers struggled with this cosmic game of hide and seek until they developed algorithms sensitive enough to detect the subtlest stellar wobbles and light dips caused by orbiting worlds. But these planet-hunting tools didn't stay confined to telescopes. They've quietly infiltrated our daily lives, powering everything from medical diagnostics to your streaming recommendations. The same math that spots alien worlds now helps doctors spot tumors and predicts whether you'll need an umbrella next Tuesday. Take the transit method, which looks for periodic dimming as planets pass in front of their stars. To separate real planetary signals from stellar flickers or instrument noise, astronomers developed machine learning models that analyze thousands of light curve features simultaneously. These same models, trained on cosmic data, now pass medical scans with superhuman precision, spotting early-stage cancers in mammograms by recognizing patterns too subtle for human eyes, just as they once identified exoplanets hidden in stellar noise. The Kepler Space Telescope's data pipeline, designed to flag potential Earth-like worlds, became the foundation for AI systems that now monitor premature babies' vital signs, predicting infections hours before symptoms appear. Then there's radial velocity detection, measuring how a star's spectrum shifts as planets tug it back and forth. The algorithms that disentangle these subtle wavelength changes from atmospheric interference now enhance speech recognition software. Your smart speaker's ability to hear "play jazz" instead of "play gas" owes its accuracy to stellar spectroscopy techniques repurposed for parsing human voices amid background noise. Even more impressive, these adapted algorithms help seismologists predict aftershocks by detecting infinitesimal ground vibrations, much like they once teased out planetary signals from stellar jitters. Recommendation engines reveal perhaps the most unexpected crossover. When the European Space Agency's Gaia mission mapped over 1 billion stars, its classification system designed to group stars by similar properties inspired the clustering algorithms that now power streaming platforms. That's why when you finish watching a documentary about black holes, your suggested queue fills with physics lectures and sci-fi movies. The cosmic becomes personal as stargazing tools curate your entertainment. What makes this transfer of knowledge so powerful is the shared challenge of pattern recognition in noisy environments. Whether distinguishing a planet's gravity from stellar activity or identifying a tumor in cluttered tissue, the core problem remains: find the meaningful signal buried in chaos. As AI systems trained on celestial data tackle earthly problems, They're proving that the universe's complexity and our own are cut from the same mathematical cloth. The next time your weather app warns of an approaching storm, remember, it's thinking like a planet hunter, tracing patterns in atmospheric turbulence just as it once traced orbits in starlight. The most profound impact might be yet to come, as astronomers develop new techniques to identify biosignatures, chemical traces of life in exoplanet atmospheres. These methods are being adapted to detect disease markers in human breath. Soon, a single exhale analyzed with algorithms descended from space telescopes could diagnose cancer or infections as easily as we spot oxygen on distant worlds. The tools built to explore the cosmos are becoming mirrors, reflecting back insights about ourselves we might never have discovered otherwise. In teaching machines to read the universe, we've given them the language to understand our own world. Our sun may seem steady and reliable, but it has a temper. Every so often, it hurls billion-ton clouds of magnetized plasma into space, solar storms powerful enough to knock out satellites, scramble radio signals, and even plunge entire cities into darkness. The most infamous example hit in 1859, when a solar superstorm sparked auroras so bright they woke people in the Caribbean, while telegraph systems burst into flames from induced currents. If a similar storm struck today, experts estimate it could collapse power grids for months, triggering trillions in damages. But here's the twist. The same violent space weather that threatens our technology has also taught us how to protect it, thanks to an unlikely partnership between astrophysicists and electrical engineers. The breakthrough came from studying not just our sun, but dead stars that behave like cosmic storm machines. Magnetars, neutron stars with magnetic fields a quadrillion times stronger than Earth's emit flares so powerful they can disturb Earth's ionosphere from 50,000 light-years away. By analyzing these extreme events, scientists recognized patterns also present in solar storms. Twisted magnetic field lines that suddenly snap, releasing unimaginable energy. This insight led to early warning systems that now monitor the sun's surface for telltale magnetic instabilities, giving grid operators precious minutes to shut down vulnerable transformers before a storm hits. Transformers themselves got a redesign inspired by cosmic resilience. Engineers realized that neutron stars cope with magnetic chaos by channeling energy along crystalline structures in their crusts, a principle adapted into grid-scale superconducting fault current limiters. These devices, embedded in modern power stations, absorb surges like cosmic shock absorbers, mimicking how magnetars dissipate energy without catastrophic failure. Even the humble surge protector in your home owes its design to models of how pulsars filter out electromagnetic noise while maintaining stable rotation. The most ingenious solutions cross-pollinate celestial and terrestrial wisdom. During solar storms, Earth's magnetic field vibrates like a plucked string, inducing currents in pipelines and power lines. Geophysicists studying similar vibrations from distant supernova developed algorithms that now help grid operators distinguish between dangerous geomagnetic disturbances and harmless fluctuations. Meanwhile, satellite shielding tested against simulated magnetar radiation protects sensitive electronics in everything from undersea internet cables to hospital MRI machines. What began as a survival strategy has blossomed into an unexpected advantage. Solar storm research spawned advanced materials like metal oxide varistors, which guard against voltage spikes in renewable energy systems. Techniques for predicting space weather now optimize wind farm layouts by modeling turbulence like solar wind patterns. And the same simulations that track coronal mass ejections help stabilize smart grids, balancing supply and demand with cosmic precision. The lesson is clear. The universe doesn't just throw problems at us, it encodes the solutions in its extremes. By listening to stars both living and dead, we've turned existential threats into blueprints for resilience. Every time you flip a switch without a second thought, remember, you're benefiting from hard-won wisdom whispered across the solar wind, a reminder that even the heavens' fury can light our way forward. Above our heads, a silent crisis orbits at 17,000 miles per hour, a growing cloud of discarded rocket parts, dead satellites, and fragments from decades of space exploration. What was once considered humanity's greatest achievement now threatens to trap us on Earth, with collisions spawning more debris in a runaway chain reaction known as the Kessler syndrome. But here's the cosmic irony. The same astrophysical principles that explain how dead stars recycle themselves into new planets might hold the key to cleaning up our celestial backyard. Nature has been solving this problem for billions of years, and we're finally learning to speak its language. Take planetary formation. When massive stars die in supernova, their scattered remnants don't just vanish, they become the raw materials for new worlds. Dust grains collide gently in protoplanetary disks, sticking together through electrostatic forces until they snowball into asteroids and planets. Scientists studying this process realized something revolutionary. The same weak forces that build planets could dismantle space junk. Experimental missions like Japan's ELSA-D use magnetic docking systems inspired by cosmic dust adhesion, capturing derelict satellites with the gentleness of particles clumping in a stellar nursery. Unlike brute force solutions like harpoons or nets, these systems mimic nature's patience, turning chaos into order one fragment at a time. The parallels run deeper. Just as pulsars sweep their surroundings clean with electromagnetic beams, engineers are testing ion thrusters that nudge debris into decaying orbits using targeted plasma jets. These cosmic brooms don't eliminate junk, they guide it toward Earth's atmosphere, where friction incinerates it harmlessly, mirroring how neutron stars clear their orbits through gravitational influences. Even the algorithms predicting debris trajectories borrow from models of asteroid belt dynamics, where gravitational resonances create safe lanes amid chaos. What makes these solutions so elegant is their scalability. Nature doesn't clean entire galaxies at once, it works incrementally, focusing on local equilibriums. Similarly, startups like Astroscale deploy shepherd satellites that tend to high-risk debris clusters first, prioritizing the busiest orbital highways just as interstellar gas concentrates in spiral arms. The European Space Agency's Clear Space mission takes inspiration from cosmic recycling on an even grander scale, planning to repurpose debris into new structures using in-orbit 3D printing, a technique echoing how supernova remnants condense into new stellar systems. The ultimate goal isn't just cleanup, but a paradigm shift. In nature, nothing is truly wasted. Every exploded star becomes feedstock for future generations. Companies like OrbitFab are pioneering this mindset with orbital gas stations that refuel satellites instead of discarding them, while NASA's Awesome One mission will retrofit old satellites with new tech mid-flight. These projects transform debris from trash into a resource, just as interstellar clouds transform stellar ashes into rocky worlds. Perhaps the most poetic twist comes from biomimicry. Certain bacteria extract metal ions from solution to build protective shells, a process now guiding experiments in self-assembling debris shields. Imagine satellites that grow their own micrometeoroid armor by harvesting aluminum from nearby fragments, like cosmic mollusks building shells from stellar debris. This closed-loop approach doesn't just solve a technical problem, it honors the universe's fundamental truth that destruction and creation are partners in an endless dance. As we look to the stars for answers, we're reminded that space was never empty. It's a dynamic ecosystem where gravity, magnetism, and chemistry collaborate to maintain balance. Our challenge isn't just engineering better tools, but learning to think like the cosmos, seeing every bolt, every spent rocket stage, not as waste, but as raw potential waiting to be reborn. The same forces that sculpted galaxies from stardust may yet teach us how to turn our orbital junkyard into a thriving, sustainable frontier. The silence of the cosmos isn't just a scientific puzzle, it's a mirror reflecting our own technological adolescence back at us. The Fermi paradox, that haunting question of why we see no signs of advanced alien civilizations despite the universe's vast age, forces us to confront an unsettling possibility. What if the reason we haven't detected others is because all sufficiently advanced civilizations inevitably develop technologies that render them invisible? This isn't science fiction, it's a real ethical crossroads we're approaching ourselves as humanity's own electronic whispers begin their journey across the galaxy. Consider the timeline. Our first intentional interstellar message, the Arecibo transmission of 1974, has traveled less than 50 light-years, a mere speck in our galactic neighborhood. Yet already, our planet leaks radio, television, and radar signals into space like an unshielded beacon. Early episodes of I Love Lucy now wash over star systems nearly 70 light-years away, while military radars from the Cold War era continue announcing our presence to any listeners within a 100 light-year radius. But here's the twist: as our technology matures, we're actively becoming quieter. Fiber optics replace broadcast towers, encrypted digital signals mimic cosmic noise, and directional lasers enable precise communication that doesn't bleed into space. The same progression that makes our civilization more advanced may also make it undetectable from afar, a potential solution to the Fermi paradox hidden in plain sight. This cosmic hide-and-seek game raises profound ethical questions about humanity's galactic footprint. Should we deliberately broadcast our existence, as the messaging extraterrestrial intelligence advocates propose? Or does our own lack of detected signals suggest that advanced civilizations learn to cloak themselves for protection? The parallels to internet security are striking just as we now understand the dangers of oversharing personal data online. Might there be existential risks in broadcasting planetary-scale information into the void? Some astrophysicists argue that the Great Filter, the hypothetical barrier preventing civilizations from becoming interstellar, could be technological self-destruction or technological disappearance. The artifacts we're leaving behind add another layer to this puzzle. Voyager's golden record, etched with human greetings and Earth sounds, will outlive our species by billions of years. SpaceX's Tesla Roadster, launched toward Mars orbit in 2018, might eventually become the oldest recognizable human-made object in the solar system. These aren't just curiosities, they're test cases for how civilizations might choose to represent themselves across cosmic time. The same ethical framework guiding museum curators preserving ancient artifacts now informs debates about what humanity should leave for future galactic archaeologists or potential discoverers. Perhaps the most humbling realization is how our search methods shape what we find. For decades, SETI focused on radio waves because that was our dominant technology, like someone searching for smoke signals while missing fiber optic cables. New initiatives like Breakthrough Listen now scan for laser pulses and other exotic signatures, acknowledging that advanced civilizations might communicate in ways we're only beginning to imagine. This technological humility mirrors our growing awareness that alien minds might perceive reality through entirely different sensory frameworks, making mutual recognition far more complex than simply tuning to the right frequency. As we refine our ability to listen to the cosmos, we're simultaneously grappling with whether and how to speak back. The decisions we make today about encryption standards, signal leakage, and interstellar messaging will echo for millennia, carried forward on electromagnetic waves that outlive continents. In wrestling with the Fermi paradox, we're not just searching for aliens, we're deciding what kind of civilization we want to become, and how we'll present humanity's story to whatever or whoever might eventually be listening. The greatest legacy of our technology may not be what it allows us to find, but what it teaches us about stewardship on a galactic scale. Two particles born from the same quantum event can find themselves on opposite sides of the galaxy, yet remain mysteriously linked. Change one, and its twin instantaneously reflects that change, as if space and time between them don't exist. Einstein famously dismissed this phenomenon as spooky action at a distance. But today, we know it's not just real, it's the universe's most intimate handshake, a cosmic thread woven into the fabric of reality itself. And nowhere is this entanglement more extreme than in the wreckage of dead stars, where neutron stars spin with such perfect synchronicity that they've become nature's blueprint for the next technological revolution. Inside a neutron star's crushing gravity, particles don't just interact, they merge into quantum soups where individual identities blur. Electrons and protons fuse into neutrons so densely packed that their quantum states become shared across the entire star, creating a single, entangled entity. When these stars collide or form binary pairs, their particles remain linked across thousands of miles, whispering to each other through what physicists call non-local connections, the same phenomenon that now powers quantum computers here on Earth. The leap from stellar oddity to lab breakthrough came when researchers realized entanglement could solve computing's greatest bottleneck, information speed. Traditional computers shuttle data along wires limited by the speed of light, but entangled particles communicate instantly, regardless of distance. Companies like IBM and Google now harness this by creating quantum bits qubits that mirror neutron star behavior. In a lab chilled near absolute zero, superconducting loops mimic the paired spins of particles in a pulsar's core, processing calculations that would take conventional machines millennia. What makes this cosmic theft so transformative is error correction. Neutron stars maintain coherence despite existing in the universe's noisiest environments. Their particles resist decoherence through natural feedback loops. Quantum engineers copied this by arranging qubits in topological lattices, where errors cancel each other out like vibrations in a cosmic gyroscope. The result: quantum processors that, like pulsars, grow more stable under pressure. Yet the true marvel lies in how entanglement bridges scales. A single neutron star's quantum links span city-sized masses, while lab qubits manipulate atoms. Both exploit the same physics, reality's hidden interconnectedness. As we tap into this, we're not just building faster computers, we're learning to navigate reality's deepest layer, where the universe itself operates as one vast, entangled network. The stars didn't just show us the phenomenon, they perfected its use over billions of years. Now, their ghosts are teaching us to rewire the future. Every time your phone pinpoints your location on a map, it's silently correcting for distortions in the very fabric of time itself, a phenomenon first predicted by Einstein and later confirmed by the eerie behavior of dead stars. Those navigation satellites 20,000 kilometers above you experience time slightly faster than we do on Earth's surface, gaining about 38 microseconds each day because they're farther from our planet's gravitational grip. Without accounting for this relativistic drift, your GPS location would accumulate errors at roughly 10 kilometers per day, turning your morning commute into a cosmic guessing game. The irony is exquisite. The same physics that governs the warped spacetime around neutron stars where gravity is so intense it bends light into pretzels also influences the atomic clocks aboard orbiting satellites. Each tick of those ultra-precise timekeepers must be adjusted not just for the speed at which satellites zoom around Earth, which slows their clocks via special relativity, but also for their altitude, which speeds up time via general relativity. The net effect requires engineers to deliberately build clocks that run slightly slower on the ground, so they'll synchronize perfectly in orbit. It's as if we've tricked time itself by reverse engineering the universe's hidden rules. Dead stars served as the ultimate proving ground for these calculations. When astronomers discovered the first binary pulsar system in 1974, they noticed its orbiting neutron stars were spiraling together exactly as Einstein's equations predicted, losing energy through gravitational waves that subtly alter their clocks. This cosmic confirmation gave GPS engineers the confidence to bake relativity into their systems decades before quantum physics became mainstream. Today, your phone's location services effectively perform miniature versions of those pulsar timing experiments, comparing signals from multiple satellites to triangulate your position within meters. But the story doesn't end with simple corrections. Modern systems now harness these relativistic effects creatively. The European Galileo navigation system exploits time dilation to enhance accuracy, using the slight timing differences between satellites to detect and correct for atmospheric interference automatically. Similarly, military-grade GPS receivers analyze relativistic discrepancies to distinguish between authentic satellite signals and potential spoofing attempts. What began as an esoteric consequence of Einstein's theory has become both a technical hurdle and an unexpected security feature. Perhaps most remarkably, these adjustments have revealed hidden layers in spacetime itself. Tiny discrepancies between predicted and observed satellite clock behavior led physicists to discover subtle variations in Earth's gravitational field, clues about underground water reservoirs and magma movements. Like cosmic doctors, we're now using relativistic GPS data to take the planet's pulse, detecting earthquakes before they strike by monitoring how they distort the fabric of spacetime. The same principles that keep your pizza delivery on track might one day predict volcanic eruptions. This convergence of stellar physics and everyday technology underscores a profound truth. The universe doesn't operate in separate realms of theoretical and applied science. A dead star's gravitational whisper and your phone's navigation accuracy are threads from the same cosmic tapestry, woven together by equations scribbled a century ago by a patent clerk who dared to reimagine time itself. As you glance at your map app tomorrow, remember, you're not just seeing your location, you're witnessing the afterlife of starlight, transformed into guidance through the invisible geometry of reality. Deep in the vacuum of space between the stars floats a treasure more valuable than gold cosmic dust. These microscopic particles, no larger than a wavelength of light, are the shattered remains of ancient supernova and colliding asteroids, drifting for eons before gently settling on Earth. But these aren't just inert specks, they're nature's blueprints for some of the most advanced materials we've ever created. The same stardust that once seeded planets with the ingredients for life is now revolutionizing nanotechnology, proving that the universe's smallest debris holds its biggest secrets. Take graphene, the wonder material stronger than steel yet thinner than a single atom. Its discovery earned a Nobel Prize, but its inspiration came from the cosmos. Meteorites recovered from Antarctica and Siberia contain carbon structures eerily similar to graphene natural nanosheets forged in the extreme pressures of dying stars. When scientists examined these cosmic samples under electron microscopes, they noticed something extraordinary. The carbon atoms arranged themselves in perfect hexagonal lattices, just like lab-grown graphene. The universe had been crafting nanomaterials billions of years before we even knew they existed. This cosmic connection goes deeper than mimicry. Some interstellar dust grains exhibit ultra-strong properties due to their unique crystalline defects, tiny imperfections that counterintuitively make them more resilient. Materials scientists are now deliberately engineering similar defects into synthetic nanomaterials, creating ceramics that resist shattering and metals that heal their own cracks. It's as if Supernova left behind instruction manuals for building at the smallest scales, and we're just now learning to read them. Then there's conductivity. Certain types of cosmic dust, particularly those rich in silicon carbide, display quantum behaviors at room temperature, phenomena we usually only observe in ultra-cooled lab conditions. These particles act like natural quantum dots, funneling electrons with near-perfect efficiency. Solar panel manufacturers have taken notice, incorporating nanostructures inspired by these interstellar semiconductors to boost energy conversion rates. The same stardust that once blocked light in ancient nebulae now helps harness sunlight on Earth. Perhaps the most startling application lies in medicine. Nanoparticles derived from meteoritic iron exhibit magnetic properties so precise they can navigate bloodstreams like microscopic submarines. Researchers coat these particles with antibodies, then guide them with external magnets to deliver drugs directly to tumors, a technique dubbed cosmic chemotherapy. Early trials show these star-borne particles can target cancer cells with twice the precision of conventional methods, all while minimizing side effects. Who knew the debris of dead stars might one day cure living bodies? The real magic happens when we stop seeing cosmic dust as mere residue and start recognizing it as the universe's oldest nanotechnology lab. Every year, thousands of tons of this extraterrestrial material rain down on Earth, each grain a frozen experiment in extreme physics. Some contain buckeball soccer ball-shaped carbon molecules that inspire new lubricants and superconductors. Others harbor perovskite crystals that could revolutionize renewable energy storage. There's even evidence that certain prebiotic molecules, the building blocks of life, hitched rides on these microscopic space travelers. What began as curiosity about dusty meteorites has blossomed into a new frontier in materials science. Laboratories now simulate interstellar conditions to grow astromaterials in vacuum chambers, replicating the cold, radiation-drenched environments where cosmic dust forms. The resulting structures often defy conventional physics, exhibiting properties we can't yet fully explain. It's a humbling reminder that for all our advances, the universe retains mastery over the very small. So the next time you brush a speck of dust off your sleeve, pause for a second. That tiny particle might carry echoes of an explosion that lit up the galaxy millions of years ago, and the secrets to technologies we've only begun to dream of. The cosmos doesn't just surround us, it's woven into the fabric of our world, whispering lessons in resilience, efficiency, and innovation at scales we're only now learning to see. A black hole doesn't just consume light, it sculpts it into a cosmic magnifying glass. When light from distant stars passes near these ultra-dense remnants, the black hole's gravity bends the light's path, warping and amplifying it like a lens. This phenomenon, called gravitational lensing, turns dead stars into nature's telescopes-free, floating observatories that reveal galaxies too faint for our instruments to detect alone. But here's the twist: we didn't just observe this celestial trick. We stole it, reverse engineering the universe's light-bending secrets to revolutionize how we see everything from distant supernova to the human retina. The breakthrough came when astronomers realized they could mimic gravitational lensing on Earth. Just as a black hole's warped space-time focuses light, deformable mirrors in telescopes can counteract the blurring effects of Earth's atmosphere. This technology, called adaptive optics, uses real-time measurements of atmospheric turbulence, often by tracking a bright, guide star, or even firing a laser to create an artificial one to reshape the mirror's surface hundreds of times per second. The result, images so crisp they can spot a car's headlights on the moon or track individual stars orbiting the supermassive black hole at our galaxy's center. But the cosmic inspiration didn't stop at astronomy. The same principles that sharpen telescope views now correct vision in ways glasses and contacts never could. In laser eye surgery, adaptive optics systems map the unique distortions in a patient's cornea, then guide lasers to reshape it with microscopic precision. It's gravitational lensing in reverse. Instead of bending light through warped space-time, we're bending the eye itself to focus light perfectly. Surgeons even use these systems to image individual retinal cells, catching diseases like glaucoma or macular degeneration before symptoms appear, diagnostics as precise as spotting a planet orbiting a star light years away. The most astonishing applications lie in microscopy. Biologists studying living cells face the same challenge as astronomers peering through Earth's atmosphere, turbulent distortions, in this case from fluids and tissues. By adapting telescope technology, researchers now peer deep into organs or embryos without slicing them open, revealing processes like neuron firing or cancer metastases in real time. One team even combined adaptive optics with gravitational lensing's other lesson, light amplification, to visualize proteins so small they were previously invisible, like using a black hole's magnification to read a newspaper on another planet. What makes this cosmic theft so elegant is its scalability. The universe doesn't care whether it's bending starlight or the light from a single cell, the physics remains the same. Engineers have miniaturized adaptive optics into endoscopes thinner than a human hair, while astronomers deploy stadium-sized versions to hunt for Earth like exoplanets. The same algorithm that stabilizes a telescope's view also reduces blur in smartphone cameras, proving that dead stars' gifts aren't confined to labs or observatories. Yet the greatest lesson isn't just about sharper images, it's about perspective. Gravitational lensing reminds us that distortion isn't noise to eliminate, but information to decode. When a black hole bends light, it imprints details about its mass and spin onto the distorted image. Similarly, modern optics analyze how light scatters to reconstruct 3D maps of everything from ocean floors to brain tissue. The universe didn't just give us a better lens, it taught us to read the whispers hidden in the warps. As we push these technologies further, we're blurring the line between observation and creation. Next-gen telescopes will use deformable mirrors to cancel out starlight, exposing orbiting planets like removing glare from a windshield. Meanwhile, surgeons are testing smart scalpels that adjust in real time to a patient's unique tissue distortions, as precise as a pulsar's beam. The light-bending tricks of dead stars have become a universal language, one that lets us see, heal, and explore in ways that once belonged solely to the cosmos. Between the cacophony of pulsars and the background hum of the Big Bang, there exist pockets of cosmic quiet, regions where the universe seems to hold its breath. These silent zones, often found in the voids between dead stars or the cold stretches of interstellar space, aren't just empty. They're nature's perfect listening rooms where the absence of noise becomes its own kind of signal. For astronomers hunting for extraterrestrial intelligence, these quiet patches are golden. They're where faint whispers from distant civilizations might finally rise above the cosmic static if we know how to listen. The challenge isn't just finding silence, it's learning to use it. Imagine trying to hear a single violin in a stadium full of roaring crowds. That's the dilemma SETI researchers faced for decades until they realized dead stars offered a solution. Pulsars, with their predictable rhythms, act like cosmic metronomes. Their steady beats provide a reference to filter out interference. By tuning receivers to ignore these known signals, scientists effectively mute the universe's loudest instruments, leaving behind cleaner bandwidth to scan for anomalies. This technique, called matched filtering, now helps your phone distinguish your voice from background noise during calls. The same math that hunts aliens also powers voice assistants like Siri and Alexa. But the real magic lies in what these quiet zones reveal about focus. In the 1960s, radio astronomers discovered that certain frequencies between hydrogen and hydroxyl emissions, dubbed the water hole, were unusually serene. These bands, coincidentally where the building blocks of life emit radio waves, became prime hunting grounds for alien signals. The lesson: sometimes progress isn't about adding more data, but strategically subtracting noise. Tech companies took note. Modern noise-canceling headphones use similar principles, analyzing ambient sound waves and generating inverse frequencies to silence them. It's cosmic signal processing miniaturized for your commute. The philosophical implications run even deeper. Just as interstellar silence helps us hear potential alien greetings, personal quiet can sharpen our attention in an overwhelming world. Studies show that intermittent digital detoxes, moments of deliberate disconnection, boost creativity and problem-solving, much like how radio telescopes perform better when shielded from Earth's electronic chatter. The universe's quiet zones aren't just physical, they're metaphors for the mental space needed to recognize what truly matters. Perhaps the most profound application lies in machine learning. Training AI to recognize faint signals, whether alien transmissions or early signs of disease in medical scans, requires teaching algorithms to embrace stillness. By feeding neural networks cosmic noise datasets alongside intentional signals, engineers mimic how astronomers train their ears on the universe's silences. The result: systems that detect breast cancer from mammograms with superhuman accuracy, or spot manufacturing defects invisible to the human eye. The quieter the background, the clearer the signal, whether it's a hello from another star system or a life-saving diagnosis hidden in pixels. As we push further into the cosmos, these lessons only grow more vital. Next-gen telescopes like the Square Kilometre Array will harness dead stars' quiet neighborhoods to listen for technosignatures, the hypothetical fingerprints of advanced civilizations. Meanwhile, back on Earth, the same principles refine everything from earthquake prediction to financial fraud detection. The universe's silent stretches aren't voids, they're canvases where faint but vital patterns emerge. In learning to appreciate cosmic quiet, we've unlocked new ways to hear, see, and understand, not just out there, but within our own noise-choked world. Deep in the swirling clouds of stellar nurseries, where new stars ignite from collapsing gas, nature performs a kind of alchemy we're only beginning to replicate on Earth. These cosmic cauldrons don't just forge suns, they spin intricate webs of dust and plasma, sculpting structures with fractal precision under forces that balance turbulence and gravity in a delicate dance. What's astonishing isn't just the beauty of these formations, but how their underlying physics now guides one of our most cutting-edge technologies, 3D printing. The same chaotic forces that shape star-forming regions are helping engineers design materials with impossible geometries, layer by layer, atom by atom. Take the way interstellar gas behaves under extreme conditions. As gravity pulls matter inward, magnetic fields and turbulent eddies twist the collapsing material into spiraling filaments, a pattern eerily similar to the lattice structures in advanced 3D printed metals. Researchers studying these cosmic whirlpools realized something revolutionary. turbulence isn't just an obstacle to overcome in manufacturing, it's a design tool. By mimicking the natural self-organization of stellar nurseries, engineers now use controlled chaos to strengthen printed materials. Imagine a jet engine turbine blade, its interior not solid metal but a swirling microlattice inspired by the Orion Nebula's gas tendrils, lighter than aluminum yet stronger than steel. The real breakthrough came from plasma physics. In star-forming regions, ionized gas doesn't just flow, it sculpts. Electrically charged particles follow magnetic field lines like beads on a cosmic abacus, creating intricate arches and loops. Scientists at institutions like MIT and ESA have adapted this principle to directed energy deposition, 3D printing, where charged particle beams build objects in midair, layer by layer, without traditional supports. The result: aerospace components with internal cooling channels that mimic the fractal veins of a leaf or the branching structures in nebula clouds, designs impossible to manufacture until we borrowed the universe's blueprint. But the most poetic crossover lies in material properties. The dust grains in stellar nurseries are anything but uniform. They're jagged, porous, and layered, with surfaces pocked by eons of cosmic radiation. These imperfections, it turns out, make them extraordinary catalysts for chemical reactions. Materials scientists now intentionally replicate these flaws in 3D printed catalysts, engineering nanoscale roughness that boosts efficiency in everything from hydrogen fuel production to pharmaceutical synthesis. A team at Caltech even grew synthetic meteorite dust in the lab, using its peculiar structure as a template for printing ultra-efficient solar cell components. The universe's debris became our innovation accelerator. Perhaps the most futuristic application involves zero-gravity printing. In space, without Earth's gravity to contend with, 3D printers can exploit fluid dynamics much like star-forming clouds do, allowing liquids and gases to self-assemble into shapes that defy conventional manufacturing. NASA experiments aboard the International Space Station have already printed human tissue and electronics using techniques inspired by how protoplanetary disks organize particles into rings and spirals. Soon, orbital factories may construct entire satellite components in ways that echo the birth of solar systems, proving once again that the cosmos isn't just a place to explore, but a mentor to learn from. The lesson is clear: creation at any scale, whether forging a star or printing a replacement heart valve, follows universal rules. By studying how the universe builds, we're not just improving technology, we're rediscovering a shared language of structure and growth, written in the mathematics of turbulence, magnetism, and self-assembly. Every time a 3D printer hums to life, it whispers an ancient truth. Innovation isn't about defying nature's laws, but embracing them. On a quiet August night in 1977, a radio telescope in Ohio picked up something extraordinary, a signal so powerful and unusual that astronomer Jerry Amon circled it in red pen and wrote, "Wow." Next to the printout, that brief 72-second burst of radio waves coming from the direction of the constellation Sagittarius carried all the hallmarks of an artificial transmission: narrow bandwidth, intense focus, and a frequency matching the hydrogen line precisely where scientists had predicted an alien civilization might send a deliberate hello. Then, just as suddenly as it appeared, it vanished, never to repeat despite decades of searching. The WOW signal remains one of space's most tantalizing mysteries, but its true legacy isn't just about aliens. It's about how such cosmic anomalies force us to refine the very tools we use to listen to the universe. At its core, the WOW signal exposed the limitations of our technology. The Big Ear telescope that detected it was essentially a giant metal sheet focusing radio waves onto primitive detectors, a far cry from today's phased arrays and quantum sensors. When the signal disappeared before astronomers could triangulate its source, it sparked a revolution in observational methods. Modern SETI initiatives now deploy networks of synchronized telescopes spanning continents, allowing real-time verification of any potential signal. Breakthrough Listen, the most comprehensive search for extraterrestrial intelligence to date, scans millions of frequencies simultaneously with sensitivity 1,000 times greater than 1970s equipment. Those upgrades came directly from lessons learned that August night: how to capture fleeting signals, how to distinguish cosmic noise from potential messages, and most importantly, how to never let another wow slip through our fingers. But the signal's influence extends far beyond alien hunting. Its enigmatic properties pushed engineers to develop new ways of handling sparse, ambiguous data, techniques now embedded in technologies from medical imaging to financial forecasting. The same algorithms that sift through cosmic static for repeating patterns help radiologists spot early-stage tumors in noisy MRI scans. Machine learning models trained to recognize anomalous astrophysical signals now monitor power grids for subtle fluctuations that precede blackouts. Even your spam filter owes a debt to the wow signal. Its ability to separate meaningful signals from background chaos evolved from statistical methods astronomers refined while ruling out natural explanations for that famous blip. Perhaps most intriguing are the unexpected discoveries made while chasing wow-like phenomena. When researchers expanded the search to lower frequencies, they stumbled upon fast radio bursts, mysterious millisecond-long cosmic flashes now thought to originate from magnetars or colliding neutron stars. These celestial fireworks, some releasing more energy in milliseconds than the sun does in months, were invisible to older telescopes. Similarly, efforts to explain the wow signal's peculiar bandwidth led to breakthroughs in laser communications, paving the way for fiber optic networks that now underpin global internet infrastructure. The universe's unsolved mysteries often point toward technologies we didn't know we needed. What makes the wow signal so enduring isn't just its mystery, but what it represents: a cosmic Rorschach test revealing humanity's evolving relationship with the unknown. For some, it's proof we're not alone. For others, a cautionary tale about jumping to conclusions. But for scientists and engineers, it's something more practical, a benchmark for progress. Every time a new telescope array comes online or a fresh data analysis technique emerges, someone inevitably asks, could this finally explain wow? That unanswered question drives innovation forward, reminding us that the universe's greatest gifts often come disguised as puzzles. The next time your phone instantly connects to a satellite or a doctor catches a disease early through advanced imaging, remember, those capabilities were honed by our collective determination to solve a mystery written in static 46 years ago by a single astonished astronomer and his red pen. When two neutron stars' cosmic corpses so dense a teaspoon would weigh 1 billion tons spiral together in a final, catastrophic embrace, they unleash something far more precious than destruction: the seeds of human innovation. These kilonova explosions, among the most violent events in the universe, act as natural particle accelerators, forging rare earth metals like platinum, gold, and europium in their wake. A single collision can produce hundreds of Earth masses worth of these elements, scattering them across interstellar space like cosmic glitter. But what makes these events so extraordinary isn't just their destructive power, it's how they've become a roadmap for securing the very materials that power our modern world. Take the gold in your smartphone circuitry. Unlike lighter elements forged in ordinary supernova, gold's atomic structure requires an environment so extreme it can only form during neutron star collisions. Here's why: to create elements heavier than iron, atomic nuclei must rapidly capture free neutrons, a process called rapid neutron capture, or the R process. Neutron stars, with their unimaginable densities, provide the perfect crucible. When they collide, the resulting tidal forces eject neutron-rich material at relativistic speeds, creating a radioactive soup where atoms grow fat with neutrons before decaying into stable, heavy metals. It's cosmic alchemy on a staggering scale, one that explains why all the gold on Earth could fit into a single Olympic-sized swimming pool. Astronomers didn't just stumble upon this connection. The smoking gun came in 2017, when gravitational wave detectors and telescopes observed a kilonova in the galaxy NGC 4993. The event, catalogued as GW 170817, emitted a telltale infrared glow, the spectral fingerprint of heavy elements like platinum and uranium condensing from the expanding debris cloud. This single observation confirmed what theorists had suspected for decades. Neutron star mergers are the universe's primary foundries for rare earth metals. Suddenly, the origins of everything from jewelry to jet engines traced back to these apocalyptic dances in deep space. But the implications go far beyond mere curiosity. As demand for these metals skyrockets, gold for electronics, platinum for catalytic converters, rare earths for renewable energy, tech scientists are reverse engineering kilonovae to locate new deposits. By mapping the gravitational wave echoes of ancient collisions, researchers can predict where heavy elements might have enriched certain regions of the Milky Way. Startups like Asteroid Mining Corporation already use these celestial treasure maps to prioritize asteroid targets, since many space rocks are essentially fossilized remnants of these metal-rich explosions. The most groundbreaking work, however, happens in laboratories. Teams at facilities like the Facility for Rare Isotope Beams are recreating miniature R-process conditions using particle accelerators, hoping to synthesize scarce metals on demand. It's a daunting challenge. The energies required are astronomical, but early successes in producing short-lived heavy isotopes hint at a future where we might not need to mine asteroids or ocean floors. Imagine nuclear reactors tuned to act like artificial neutron stars, spinning straw into gold by replicating the universe's most extreme physics. What makes this cosmic connection so profound is its duality. Kilonovae are both destroyers and creators, erasing stellar remnants while seeding the cosmos with the building blocks of technology. Every time you tap a touchscreen or recharge a hybrid car's battery, you're interacting with atoms that began their existence in a maelstrom of collapsing stars, a reminder that innovation isn't just about looking forward, but decoding the universe's ancient, elemental recipes. The same explosions that once lit up distant galaxies now quietly power our world, proving that even in the ashes of dead stars, there are blueprints for the future. In October 2017, astronomers spotted something streaking through our solar system that defied all expectations. A dark, elongated object moving too fast to be bound by the sun's gravity. Named Oumuamua, Hawaiian for scout or messenger, this interstellar visitor was the first confirmed object from another star system to pass through our cosmic neighborhood. But what made it unforgettable wasn't just its origin, it was how it behaved. Unlike any asteroid or comet we'd seen before, Oumuamua accelerated as it left the inner solar system, as if propelled by some unseen force. Theories erupted like supernova. Mainstream science suggested outgassing, the idea that sunlight heated trapped gases beneath Oumuamua's surface, creating a natural thruster effect. But the object showed no visible coma or tail, the usual hallmarks of outgassing. This anomaly led Harvard astrophysicist Avi Loeb to propose a more provocative explanation. Perhaps Oumuamua wasn't a rock at all, but a piece of alien technology, a light sail or derelict probe drifting between the stars. The idea wasn't as far-fetched as it sounded. Humanity's own Starshot initiative plans to send tiny light sails to Alpha Centauri within decades. Could Oumuamua have been someone else's version of that, long before we even dreamed it up? Skeptics countered that extraordinary claims require extraordinary evidence. They pointed to Oumuamua's tumbling motion, an apparent lack of artificial radio signals, as proof it was just an oddly shaped space rock. Yet even the most conservative scientists admitted this visitor was unlike anything in our solar system, a jagged, pancake-shaped relic that may have wandered the galaxy for billions of years before crossing our path. Its very existence hinted at a universe teeming with unseen objects, each carrying secrets from distant star systems. The debate revealed less about Oumuamua and more about how we confront the unknown. For centuries, humans have projected their hopes and fears onto cosmic mysteries, from seeing canals on Mars to interpreting pulsar signals as alien messages. Oumuamua became a Rorschach test for our technological age. Was it a celestial oddity or a calling card from another civilization? The truth may remain forever uncertain, but the questions it raised are reshaping astronomy. Projects like the Vera-C Rubin Observatory now scan the skies nightly, hoping to catch the next interstellar visitor before it slips away. What's undeniable is Oumuamua's legacy, a reminder that the universe is stranger than we imagine, and that every unanswered question is an invitation to look deeper. Whether natural or artificial, this fleeting guest proved one thing: we live in a galaxy where surprises lurk in the darkness, waiting to challenge what we think we know. And the next time an interstellar traveler arrives, we'll be watching. In 1961, astronomer Frank Drake scribbled an equation on a chalkboard that would redefine our place in the cosmos. 7 simple variables, from star formation rates to the lifespan of technological civilizations, attempted to quantify the likelihood of intelligent life beyond Earth. But the Drake equation isn't just about counting aliens. It's a mirror reflecting humanity's deepest existential questions. When we peer into the vast cosmic graveyard of dead stars and silent civilizations, we're forced to confront a haunting possibility. If the universe is littered with relics of extinct species, what ensures our own technology won't become just another layer of interstellar fossils? Consider the echoes we've already left behind. The Voyager probes, carrying golden records etched with human greetings, now drift beyond our solar system. Our radio and television signals leak into space at light speed, forming an expanding bubble of electromagnetic noise 40 light-years thick. These artifacts could outlast not just our civilization, but our planet itself, persisting for millions of years after the last human breath. Yet compared to the billion-year whispers of pulsars, our technological footprint feels fleeting, like a campfire spark against a hurricane. The real test isn't whether we can shout into the void, but whether anything will remain to hear our message when the shouting stops. Dead stars offer a humbling perspective. Neutron stars rotate with such metronomic precision that their pulses will remain detectable long after our most advanced satellites crumble into dust. White dwarfs, the cooling embers of sun-like stars, preserve elemental ratios in their atmospheres like cosmic time capsules, revealing the composition of ancient planetary systems billions of years after their demise. Nature's relics endure not because they're indestructible, but because they're elegantly simple, built from fundamental physics that transcend time. Our challenge is to engineer with similar foresight, creating technologies that don't just serve immediate needs, but become legible to civilizations that might arise a million years from now. This isn't just philosophical musing, it's practical engineering. The nuclear waste warning markers at sites like New Mexico's WIPP facility were designed by anthropologists, linguists, and materials scientists to remain intelligible for 10,000 years, using symbols and materials resistant to erosion and cultural drift. Similar principles guide the Long Now Foundation's 10,000-year clock, buried deep inside a Texas mountain, which ticks once a year and chimes once a millennium. These projects recognize that true longevity requires more than durability. It demands universality, encoding information in forms that transcend language and time. The universe's most enduring messages share common traits: redundancy, simplicity, and alignment with immutable physical laws. Pulsars don't broadcast complex protocols. They emit pure, rhythmic pulses any civilization could recognize as natural lighthouses. The cosmic microwave background doesn't require decryption. It's a fingerprint of the universe's birth, readable through thermodynamics alone. As we design technologies meant to outlast us, whether deep space probes or underground knowledge vaults, we must balance human ingenuity with cosmic patience, building systems that degrade gracefully rather than collapse into obscurity. Perhaps the ultimate lesson lies in stellar life cycles. Stars don't fight entropy, they embrace it, transforming into new states when their fuel runs out. Our greatest legacy might not be preserving our current technological state indefinitely, but ensuring that whatever comes after us, whether biological, artificial, or something beyond our imagination, can reconstruct our story from the fragments we leave behind. In that sense, the Drake equation's final variable isn't just about how many civilizations exist, it's about how many leave echoes worth hearing across the chasms of space-time. From pulsars guiding satellites to supernova dust in your devices, the echoes of dead stars are everywhere. These cosmic relics aren't just history, they're active partners in innovation. Every time you check your GPS, stream a song, or even scroll through your phone, you're tapping into a legacy written in starlight. The gold in your circuitry, the precision of your clock, the magnetic fields shielding your data, all of it whispers of explosions that lit up the galaxy long before Earth existed. But this partnership goes deeper than raw materials. Dead stars teach us how to think. They've shown us that destruction breeds creation, that chaos can be harnessed, and that the universe's most enduring technologies are those that work with nature rather than against it. Take quantum computing, where we're learning to embrace uncertainty like particles in a neutron star's core, or renewable energy research, chasing the same fusion processes that power stars. Even our struggle with space debris mirrors how galaxies recycle stellar wreckage into new planets. The cosmos doesn't just supply parts, it offers a masterclass in problem solving. What's truly humbling is realizing how much we still don't know. Every breakthrough, from gravitational wave detection to asteroid mining, reveals new layers of cosmic ingenuity. Perhaps the next revolution lies in dark matter's invisible scaffolding, or in the quantum murmurs of black holes. One thing's certain: the universe has been running experiments for billions of years, and we've only just begun reading the lab notes. So the next time you marvel at a technological wonder, look beyond the human hands that built it. Trace its lineage back to the stars that forged its atoms, the supernova that shaped its physics, and the silent pulsars that keep it precise. Our greatest inventions aren't just products of human genius, they're collaborations with the cosmos itself. And as we stand on the threshold of interstellar exploration and quantum leaps, remember, the universe isn't just above us. It's within us, in every click, swipe, and signal. The echoes of dead stars didn't just build our world, they're calling us to imagine what's next.